So let's take a look at question 5. Now this starts off very simply, where you've just got to find the vectors AB, AC, etc. So I'm not going to work through all of these, but for instance, A to B. Now remember when you looked at the vectors topic, it doesn't really matter that you can't visualise these vectors that are in 3 dimensions. If you want the vector AB, then of course you've got to go AO and then add on vector OB. So the vector AB will be the vector AO, add the vector OB. Now what is the vector AO? Well, it's the negative of the vector OA, which of course is the position vector A. So we've just then got to add on to that the vector OB, and that's the position vector of B there, B. So that's 2, -3, 1. If we take negative A, add on B, which is 5, 8, -6, and that of course gives us 7, 5, -5. Now I'm not going to work through all of the vectors, but you will find when you work through the others that AC is equal to 4, 2, 4, and I'll just list the others. So here are all the vectors. It's a lot of menial work here, not a lot of thinking involved in this part, but we need these for part B, which is a much more interesting question. So this is about a square-based pyramid. Now, what they haven't told us is which vertex is which, and it's easy to make the assumption that A, B, C and D form the 4 vertices of the square base, and E is the peak of this square base pyramid, but, and you will find if you'd done this, you would be wrong. Now, part B, part 1, find the length of a side of the square of base P. Now, a really bad error to make here would be to just work out the magnitude of AB and assume that this looks like AB here and here, but actually we don't know that it's necessarily the case. So what I'm actually going to do is work out the magnitude of each of these vectors and see what we get. So remember, to work out the magnitude of a vector, it is essentially Pythagoras' theorem. In 3 dimensions, you can ignore any negative signs because the values are being squared. So the magnitude of AB is √99. We just don't know which vertices are A and B. So I'm going to work out the magnitude of all the other vectors as well. So here are the magnitudes of each of these vectors. Now, from here, we can deduce, looking at these, that the vertices are going to be positioned so that we have A and C adjacent and C and D adjacent. Now, how do I know this? Well, AD has a length of √72, and we know that AC is √36, as is CD. Now, √36 squared is 36, plus √36 squared, also 36, gives us 72, which of course means by Pythagoras' theorem, these 3 values fit together. Now, looking at the values of AB, BD and BC, it's clear B has got to go up here and E has got to go here to make this work. So, B part 2. Actually, B part 1, the length of a side of the base is √36 or 6. Now, part 2, the cosine of the angle between one of these edges here and the base, well, here we go. So I'll draw in my right angle triangle, call this angle theta that we're looking for. Now we know that AB is √99. And if I call this point here the midpoint of AD, we'll call that O, then we know that AO is equal to a half of AD, which is a half √72, which of course is 3√2. Now remember, you've got to be able to do this without a calculator as well. So we know that cos of theta is equal to the adjacent AO divided by the hypotenuse AB. So that's 3√2 divided by √99. And of course, that simplifies. So we end up with √2 over √11. You can rationalise the denominator as well, √22 over 11. Now, part 3, we've got to work out the height of P. Well, That can be done in a number of different ways. We know that AO is 3 over root 2. We know that this hypotenuse is root 99. So making use of Pythagoras' theorem, we know that OB squared plus 3 root 2 squared is root 99 squared, or just 99. So that's OB squared plus 18 equals 99. So OB squared is equal to 81, and the height of this pyramid is equal to 9. Now, part 4, the position vector of E. Now I'm going to make use of some maths that you will cover in the further maths specification, which you may not have seen yet. And it's all to do with vectors. Now imagine you have a line. We know how to find the Cartesian equation of a line. We can also find the vector equation of a line. Now, the vector equation of a line is of the format r equals a plus lambda p. Now, a is the position vector of a point on that line. So imagine this is the origin, and imagine a is a point on the line. This would be a vector to get us onto the line. Lambda is some kind of numerical value, and p is a vector that's parallel to the line. The idea being that r, the position vector of any point on the line, which would look like that, is equal to a plus a multiple of p, which gets you to your point there. Now, what I'm going to do is I'm going to find the vector equations for the lines AE and ED. Now, why am I working with vector equations rather than Cartesian equations? Well, the algebra is significantly easier to work with when we're dealing with vector equations. It's something you may not have seen yet, but once you see it, you will probably come to the same conclusion yourself, that things work a lot easier in their vector format. So, let's start with the line AE. Now, to get its vector equation, R, equals a plus lambda p. So a position vector of a point on the line, well, I can use little vector little a here. And then I have lambda. Now I need a vector that's parallel to my line AE. Now what vector is parallel to that? That's vector CD. So here we go. Now that's a plus lambda CD. Now we know that a is -2, 3, -1. Lambda, now what is the vector CD? Well, we found it earlier on. It's 4, -4, -2. And what I can do is I can combine these as a single vector, combining the I components, the j component, and the k component. And that's why working in Cartesian form would be really difficult here, because we're working in 3 dimensions. It's much easier to work with vectors in 3 dimensions than in Cartesian coordinates. So now I want the vector equation of the line ED. So R is equal to, now I need the position vector of a point on that line, so I'm going to use point D. And then I need to use a different constant here because it's a different line. And I need a line that is parallel, or a vector that is parallel to ED. So I'm going to use AC. That's parallel to ED. So plus mu multiplied by AC. So we know the value of D, it's 611, plus mu multiplied by the value of AC, the vector AC, which we found earlier on, it is 424. And again, I'm going to combine that as a single vector, 6 plus 4 mu, 1 plus 2 mu, and 1 plus 4 mu. Now, at point E, we know that these two must have exactly the same position vector because they intersect. So at point E, I can equate these, -2 plus 4 lambda, 3 minus 4 lambda, -1 minus 2 lambda, and I can produce interestingly, 3 pairs of simultaneous equations. So I get -2 plus 4 lambda equals 6 plus 4 mu. And that's going to simplify down to give me... Actually, no, I'm going to leave that exactly as it is for the moment. And then we'll work out the other equations as well. So 3 minus 4 lambda equals 1 plus 2 mu. And then the third one, -1 minus 2 lambda equals, and I think there should be a plus here, 1 plus 4 mu. Now, equations 1, 2 and 3. We have more equations than we need here. We have 2 unknowns and 3 equations. So all I'm going to do is add together equations 1 and 2, and we'll keep equation 3 in reserve as a check. So add equations 1 and 2, and then this gives you 1 equals 7 plus 6 mu. So from here it's very easy to solve that mu equals -1, substitute back into either equation, lambda equals +1. Now, whenever we have this situation where we have 3 sets of equations and 2 unknowns, because we only used equations 1 and 2, we need to check that the answers are still consistent with equation 3. So we're going to check in equation 3. So the left-hand side wants us to work out -1 minus 2 lambda, which is -3, and the right-hand side is 1 plus 4 mu, which is also -3. So the equations are consistent. Now, we can take our values of mu and lambda and we can substitute back into either of these to give us the position vector of point E. So OE, it doesn't matter which you pick, substitute into either of them and you will find E is equal to 2, -1, -3. So the last part tells us that we have a second pyramid attached to the first pyramid and we need to find the position vector of this vertex, which we'll call Q. Now, how do I do that? My diagram doesn't look great here, but if we look at the relationship between the coordinates of B and the coordinates of O, this will tell us everything we need. Now, the coordinates of O, well, O is the midpoint of AD, so we can simply take the average, the mean of the coordinates of AD. So that gives me 2, 2 and 0. So A's coordinates, remember your coordinates are the same numerical values as your position vector. So that's -2, 3, -1 for A, and for D that is 6, 1, 1. So take the average of those and you get 2, 2, 0. Now B's coordinates up over here are equal to 5, 8, -6. So effectively, we just have to look at the gap between the x-coordinate, the y-coordinate, and z-coordinate between O and B, and then repeat that, but in the opposite direction. So the coordinates of Q, look at the x-coordinate of O and the x-coordinate of B. There's a gap of 5. There's a gap of 3 from 2 to 5. Let's repeat that gap, but in the other direction. So rather than adding 3 to 2, we'll subtract it, which gives us an x-coordinate of -1. And let's now look at the y-coordinates of O and B. Well, there's a gap of 6 there, a difference of 6. Let's now subtract that, so that gives us -4. And then we have 0 to -6, so this time we have to add to be in the opposite direction. Remember, the visual I've sketched here is not a representation of the exact position of this object. You cannot sketch 3-dimensional space very easily, so this could be rotated in any direction. So -1, -4 and 6, those are the coordinates of this other vector, this other point, and we need to give the position vector, so we simply write it as -1, -4 and 6.